course dedicated to discovering pathways for a sustainable world. This course will present the state of the world and the different options for finding sustainable solutions. It is composed of two main parts. The first part is dedicated to the problem space. That is to say, what is the nature and complexity of the issues we face, and then a presentation of key concepts, orders of magnitude, and main principles. In the second phase, once we have assimilated all these concepts and principles, we can focus on solutions, that is, what are the pathways and characteristics of possible solutions, and what skills are necessary for their construction. In this first course dedicated to the problem space, we will start with a concept you have probably already heard of, the Anthropocene. For its introduction, I would like to quickly present a few images that clearly illustrate this general theme that humanity has domesticated the Earth. In this first image, we see a forest that has been cleared to make way for agricultural crops. It could be in Africa, it could be in Asia, it could be in Latin America. It is a scene that could be placed anywhere. In this second image, we see Mexico City. Here as well, I chose this city, but we could have chosen others. We see urban sprawl, the amount of land that has been converted to build buildings. This one might be a little less known. It's this checkerboard, this Swiss cheese. Each of these small white squares is a hole. This is a shale gas or shale oil extraction site in the United States. Each of these locations represent a drilling site where oil and gas have been extracted. And then this one, which is quite impressive, if you look closely in front of the gaping hole, the very small things, the small squares, the small rectangles, those are buildings. In fact, this open pit mine is 1 kilometer in diameter. It is a very large mine, as you can see, and it comes from Siberia. So there are not only images where humans transform nature to make it artificial. This image, which comes to us from Holland, from Oostvaardenplassen, is from Flevoland. Flevoland is a province in Holland that was built on the sea and is indeed completely artificial. It is the largest artificial island in the world, reclaimed from the sea, and now dedicated to various uses such as villages, towns, agriculture, and in its western part, a nature reserve from which this photo was taken. So, all these images show us that humanity has become a geological force, capable of transforming the Earth, and this is what we call, in a certain way, the Anthropocene. This figure represents the overall trajectory of humanity and its impact on the planet. And what we observe is that for a very long period, this impact was progressive, gradual, and then there was a sort of acceleration that roughly began around the Industrial Revolution. We measure the impacts, which we will detail later, and these impacts are increasing in such a way that humanity finds itself in a danger zone and uncertainty, which we call the planetary boundaries, the limits of the Earth. Beyond that, we do not know what might happen. This is what is called the rupture of the Anthropocene, meaning that the period we are in, the age of man, must, in a certain way, find itself within this space so that we can live in conditions that are sufficiently stable and well known to avoid problems. One of the characteristics of these limits that lead us into an uncertain future is, of course, climate change, which everyone is familiar with. There are others, and the purpose of this course is to look at them and examine the different components. This figure presents in very great detail the important characteristics of the socio-economic trends that led to a foundational concept called the Great Acceleration. This is a work that, for about 15 years, has involved looking at the various effects of humans and how we can measure them over a relatively short period of time, namely the last 2 centuries. What we observe is that the population is increasing, GDP is growing exponentially, investments are rising, fertilizer consumption is increasing, etc. All of the socio-cultural and socio-economic characteristics of the Earth system has increased exponentially since the 19th century, and within 2 generations, starting from 1950, it has multiplied by an absolutely significant factor that we will now detail. This first figure shows us the demographic evolution of humanity. What we observe is that a relatively stable growth, around 1 billion individuals, suddenly sees its slope increase, an acceleration starting from 1950, and then we are projected today at 7.8 billion, and this extremely rapid growth is happening on all continents, but mainly in Asia, over the last 30 years. This significant increase in population is accompanied by an increase in quality of life. The number of people in poverty, shown in red here, ultimately remains stable, increases a little, then decreases massively, mainly due to the rise of China. And we observe in green the number of people who are no longer in extreme poverty is increasing considerably. Populations are therefore more numerous, they have better living conditions, and they are also better educated. In this graph, the number of people with access to education who can read and write increases in blue, while the number of illiterate people in red decreases. And then it also translates to better health for everyone, because here on this graph, all the listed countries follow this type of trajectory with a more or less significant delay. The overall health of the population will increase significantly in the 20th century, with life expectancy here rising from 40 years to 80 years. Therefore, the global life expectancy of the Earth will have doubled in less than a century. This increase in the standard of living, this improvement in health and education, will also be accompanied by an increase in rights. And we observe on this slide that the countries with the highest GDP per capita on average are also those with access to the greatest number of human rights. So now if we no longer take socioeconomic indicators but instead take the planet's indicators, we observe the same thing, namely a considerable increase in a whole range of different parameters, such as the increase in carbon dioxide, a greenhouse gas, nitrous oxide, methane, ocean acidification, the number of fish caught at sea, etc. What we observe in this great acceleration is both an exponential increase in populations and quality of life, and at the same time an impact on the environment in a number of dimensions. In summary, the great acceleration refers to the fact that in 2 generations, humanity has exceeded the Earth's capacity to sustain its activities in a stable manner. This is essentially due to scientific and technical progress, the increase in communications, the extraction of non-renewable natural resources, and the considerable impacts of human activities on geology, the environment, the climate, and terrestrial ecosystems. The Gordian knot of the problem is that human prosperity today depends on economic development, which requires a tremendous amount of energy, as we will see, and this is what transforms the metabolism of the biosphere. This whole process reduces the Earth's capacity to support us. To go into a bit more detail, particularly regarding this notion of metabolism, we will recall some principles of physics and biology. The first is the law of conservation of matter. It's very simple. It's Lavoisier's law. Nothing is lost, nothing is created, everything is transformed. That is to say, all the matter that is on the planet today will be there tomorrow and was there yesterday, with few exceptions. Almost all the matter that was on Earth 4 billion years ago is still here today. I said almost, because you never know. An asteroid might fall, a satellite might leave. But all that is really epsilon-like. It's very, very small, and it's negligible compared to the amount of the Earth system. So from the point of view of matter conservation, we can say that the Earth is isolated. The second law that interests us here is the law of conservation of energy, also known as the first law of thermodynamics. It's very simple. We do not create energy, we transform it. There is no creation, there is no destruction of energy. Energy cannot be created out of nothing. It can only be transferred from one system to another. And so in a certain way, energy is the measure of a system's capacity to change a state, to produce work. Energy can transform, for example, if you are at a dam, when the water descends, you have potential energy that transforms into kinetic energy, which in turn drives the turbine, producing electrical energy. You have a transformation from one form of energy to another. but there are no cases in which you have a disappearance of energy. This notion is key because when we talk about energy in an excessive way, energy consumption or energy production, it is not entirely accurate. We should say having access to energy because it transforms, but it will always remain constant. However, the quality of energy changes. And this is due to the second principle related to energy, which is called the second law of thermodynamics. The second law of thermodynamics introduces a very interesting concept called entropy. Entropy roughly characterizes the state of disorder of a system. It is related to energy. The quality of energy in a closed system tends to decrease, to degrade. If we go back to our analogy from earlier, with the dam, we have the transformation of energy. When water is on the turbine, there are probably some frictions. It heats up a bit. This heat that is dispersed into the environment is energy lost for electrical conduction. The electrical energy that will then pass through the grid will also produce heat, and this is energy that, in quotes, degrades and is lost. So there is indeed a link between entropy disorder and the property of energy to lose its quality, again in a closed system, which is important. In this diagram, we see an illustration. If we let things happen spontaneously, the word here, the ink, will tend to diffuse, dissolve, and become unreadable because it will tend to occupy all the space. So we have a link between time, the irreversibility of time, and form, which tends to disappear, with energy, which tends to decrease in quality and degrade. So the first principle tells us that there is conservation of energy. The second principle tells us that energy over time tends to degrade. How do living beings ensure the continuity of form? At first glance, regardless of the species represented in this diagram, or if you think of any species, what does it do? It produces offspring that have roughly the same form as the parents. Over generations, this can change, it can evolve, but this maintenance of form seems, on the surface, to violate the second law of thermodynamics, since the form of living beings is not affected by time, and here there is something truly fundamental. So the key to life, and this is what distinguishes the living from the non-living, if you compare a tomato and a rock, the rock will eventually disappear over time, while the tomato will remain a tomato and produce small tomatoes that will themselves produce small tomatoes. Duplication, reproduction, and the evolution of form require matter and energy in order to sustain themselves. In fact, the thing about living beings is that they all have a metabolism, which essentially means a large number of various chemical reactions that extract energy from the environment, take matter from the environment to maintain themselves, or even duplicate and grow in size or produce offspring. This direct link between the extraction of energy and matter is what ensures to bypass or deal with the second law of thermodynamics. Because a living being is not a closed system, it uses external energy to ensure that its form is maintained. And it is the whole that will follow the second principle. So the metabolism of all living beings will excrete waste, will produce heat, which will tend to warm the environment and, in quotes, pollute it. But this is something fundamental that is intrinsic to life. Metabolism is the process by which living organisms draw energy from their environment and structure matter, using information to compensate for the increase in entropy. This is what differentiates the living from the non-living. And so, living beings being accustomed to eating each other, we have what are called trophic cascades, that is large networks with primary, secondary predators, etc. I could have shown you a forest. Here I have taken a marine ecosystem for you, in this case the Arcos, but it is exactly the same. You have the first chain, which is the chain of energy entering the system, specifically via photosynthesis, which allows plants to grow, and they themselves become the source of nutrients and energy for the first trophic level, that is, for the first organisms that eat them, then there are larger ones that will eat the smaller ones, and so on. This complex succession of trophic levels constitutes the food web, which forms an ecosystem. So in summary, photosynthesis ensures the primary access to energy, meaning that the energy from the sun enters ecosystems through plants. Until the late 1970s, it was undoubtedly believed that photosynthesis was the only way for energy to enter an ecosystem. It was discovered in the late 1970s that hydrothermal vents were themselves sources of ecosystems. Completely organized with multiple trophic networks, but independent of the sun, as they are far too deep to have access to light. And the source that has now been well identified, the source of the energy that sustains this ecosystem, is chemosynthesis, which is the transformation of molecules, in this specific case sulfur oxide, which is broken down, and this breakdown produces energy that is used by bacteria to grow. This, in symbiosis, allows the production of worms, crabs, fish, and an entire ecosystem that lives at a depth of 3,000 meters, completely disconnected from light. So it is not photosynthesis itself that is the fundamental point for creating life on Earth. It is the access to energy and the fact that it can be metabolized into forms, specifically sugars, that allow other organisms to develop. So if we now imagine all the ecosystems on the surface of the Earth, we arrive at a key concept, the concept of the biosphere, the sphere of life, which Vladimir Vernadsky introduced in 1926 in his book Biosphere. What is it? I will give you the definition here. The biosphere is the region of the Earth's crust occupied by transformers that convert cosmic radiation into active terrestrial energy, such as electrical, chemical, mechanical, and thermal energy. It is somewhat the synthesis of everything we have just seen. The transformers are living beings. In this case, we use the term cosmic radiation because chemosynthesis had not yet been discovered. However, today we could certainly extend this notion. All living beings will transform the different compartments of what we call the biosphere through the use of this energy. That is to say, three major compartments if we think about life on the surface of the planet. Life interacts with air, land, and water. And these three compartments, and living beings are therefore actually in interaction with these three compartments. And if we imagine that on the surface of the Earth it is something extremely small. Imagine the Earth. Now imagine the greatest depths. It's about 10,000 meters underwater. The highest altitude where life can be found is birds flying above the Himalayas, approximately around 10,000 meters above in the sky. So finally, on the entire Earth, the biosphere is just a very thin layer that is at most 20 kilometers thick, probably much less in most parts and covering the entire Earth. The biosphere provides a considerable number of functions for humans, and they are traditionally divided into four main functions. Support functions, the most important for us being food. Everything we eat comes from the biosphere, whether it is animal or plant-based. From provisioning functions we can, for example, obtain water, wood, or other materials that are directly derived from the production of the biosphere. Regulatory functions include, for example, the ability to purify water or air or to ensure carbon storage. And finally, cultural or social functions, because humans have a propensity to enjoy being in a natural environment, and it is an economic service, for example, to be able to go for a walk in nature or to go kayaking along a river. There is another dimension that is not mentioned here, which is very important, and that is the relationship with health. It is now known that people who have a better relationship with nature are traditionally healthier and in particular are less prone to depression. So, what is this biosphere composed of? If we take a look under the hood, what do we see? Here, in this figure, there are only eukaryotic species. Eukaryotes, that is to say, cells that have a large nucleus. This does not include viruses and bacteria, whether they are prokaryotes or archaebacteria, for those who are familiar. Among the prokaryotes and the eukaryotes present here, we have different groups. In green, it is the number of known described species, and in yellow, the species that are not described. The number of species in the biosphere is very significant. Estimates vary from one study to another. The most conservative estimates are 3 million species. On average, the consensus is rather around 8 million. And then there are some studies that suggest there might be up to 100 million. So we don't even know how many species there are on Earth. In any case, these are enormous quantities, and the majority of these species are still not described. And I'm only talking about eukaryotes, prokaryotes, and viruses. The archaebacteria are completely unexplored fields, as every time we look, we find different organisms that are not described, since they have been much less studied than eukaryotes. So we have seen the biosphere's diversity, perhaps 10 million or more species, many of which are not described. What does that represent in terms of weight in biomass? Here is a very nice work by an Israeli researcher named Ron Milo, who published The Major Masses, an estimate of what we know about the major masses of different organisms. So if we take the entirety of living organisms, the estimate is that we are roughly around 570, and the unit is gigatons of carbon. What does that mean? It means 570 billion tons of carbon. That is, each organism is reduced to what it would weigh in carbon equivalent. Well, that's for the measurement. What is important here are the different orders of magnitude. So, living organisms here account for about 570 billion tons of carbon. Out of these 570 billion, 450 are represented by plants, and primarily terrestrial plants. So the largest and by far the majority of global biodiversity in terms of mass is made up of plants. The second part is about bacteria, which is not necessarily completely trivial. Then you have fungi and viruses. And all the organisms we traditionally think of, that is animals, represent a mere 2 gigatons here, which is very low since it accounts for about 4% of the global biomass. Now, if we zoom in on this very small part and look at what it represents here, it is mainly composed of arthropods, such as insects, crustaceans, spiders, etc., which represent half, 1 gigaton, so we are looking at about 2% of the total mass. And if we look for humans, we realize that it's a very small 0.06 gigaton of carbon, which is really not much. What is even more interesting is to see that all livestock, all farming, corresponds to 0.1 gigatons, which is roughly twice the weight of humans. Wild animals represent a very small part. You can see it better in the next diagram. Here's what we are doing. In summary, for a given amount representing the entire humanity, there are about 3 times more viruses, about 3 times more worms, 12 times more fish, etc., and 7,500 times more plants. Here you have a scale representation of the number of humans on Earth, the number of livestock on Earth, and the number of wild animals, of wild mammals on Earth. A mere 4%. These figures from The Guardian come directly from the work of Ron Milo, whom I mentioned earlier. These are the same figures and the same work, but it might be a better way to understand where we stand today between the distribution given to humans, livestock, and the wild world. A very significant characteristic of the biosphere is interdependence, which is the number of relationships between organisms. This figure comes from the Northwest Atlantic, which we will discuss again shortly, and it encompasses what is called the trophic network, that is, the relationships of who eats whom among the organisms that have been identified and characterized in this part of the ocean. So, I'm obviously not going to describe everything to you. You just need to look and see that at the top there are birds and below there are fish. What is exactly at the center? And this is what will interest us. This one is the cod. We will talk about it again later. It is a fish that, as you can see, is at the center of a large network with both predators and prey. Just note the density of this network, the complexity of this network, all organisms being connected to all other organisms. It is a way to represent the interdependence of biodiversity. But this is a rather simplistic way of representing it because it only deals with who eats whom. However, there is much more to it than that. About 20 years ago, Suzanne Simard, who was studying trees in Canada, discovered that trees communicated with each other and that nutrients could pass from one tree to another. In this case, including between two different species, in this instance between the birch and the pine, communication between different trees is indeed facilitated by mycorrhizae, which are fungi. And in fact, the amount of fungi within the soil is absolutely considerable. The networks that are woven resemble the internet, and that's why this phenomenon is called the Wood Wide Web, obviously in reference to the World Wide Web. The underlying idea, the concept that has been highlighted, is that you have different species that communicate with each other and even help each other in this case. This is the case between pine and birch, which are very beautiful experiments. When you have one of the species that no longer has leaves, for example, because it is autumn and the birch loses its leaves, the pine will transmit nutrients. The pine has a problem because it is sick. At that moment, the birch will itself retransmit nutrients to it. So we have something that is of the order of symbiosis, which connects different species, mediated by fungi. It is still a formidable complexity. So we are very, very far from a simple food web here. We have links and relationships between different organisms. And then, if we want to go even further, we can try to abstract away from the organisms themselves. So here, there is a rabbit, some plants, and a mushroom. But now, what I would like is for us to focus not on the organisms themselves, but on the nutrients that pass from one to another. In this case, on this diagram, it is nitrogen. Nitrogen, there is a lot of it in the atmosphere, but it is one of the fundamental elements of life. It is essential for all living beings. And we have a problem. Living beings have a basic problem, which is the ability to capture nitrogen. There are several mechanisms. I don't want to go into detail here. What I want to emphasize is that nitrogen can be processed by bacteria to be reduced or oxidized, depending on the type of reaction. Again, I won't go into detail, but different types of bacteria produce different forms of nitrogen, and these forms may or may not be assimilated by different plants. All right, so for a given nutrient, in this case nitrogen, we have what is called a cycle that involves different types of bacteria, and all the organisms in the biosphere, which when they die, return to the soil, are degraded, re-enter a cycle, etc. So beyond the interdependence between organisms, what we see here is this notion of the nutrient cycle, and that is a fundamental concept. In fact, all the key elements of life, carbon, nitrogen, phosphorus, sulfur, oxygen, and water, perhaps with the exception of hydrogen, but that's a detail, all these key elements have the property of being in cycles within the biosphere, cycles in time and cycles in space, and they define what are called biogeochemical cycles. We have this notion of the biosphere, which includes both living organisms and compartments, such as air, water, and soil, with transformation properties. A biogeochemical cycle is the process of cyclic transport and transformation of an element or a molecule between the major reservoirs, that is, once again, water, air, soil. So, for example, if we take the case of carbon here, you have different forms released into the atmosphere, carbon dioxide or methane, but through photosynthesis, you have the possibility to capture this CO2 to promote plant growth and then enter a trophic network. It can also be dissolved in water, and then a whole series of adventures will happen to it. Among these adventures, if CO2 is dissolved in water, it can become trapped in sediments and enter the rock for a few thousand or hundreds of thousands, or even millions or hundreds of millions of years. So we have cycles that occur over extremely short timescales, like respiration and photosynthesis, and others that are extremely long, since they are geological cycles. The key notion of these biogeochemical cycles is that the essential elements of life, carbon, nitrogen, phosphorus, sulfur, and oxygen, are cycled within an ecosystem among organisms, but also, through a number of reactions, circulate between the major reservoirs such as the atmosphere, the lithosphere, and the hydrosphere. To illustrate this type of cycle, and specifically this type of oscillation, I have chosen an example from Yadvinder Mali, who has shown the primary productivity of ecosystems over a year, specifically the amount of carbon absorbed by ecosystems. Here is the image for January. As you can see, it is indeed winter in the northern hemisphere, and it is summer in the southern hemisphere. The absorption capacity is highest in southern ecosystems, particularly tropical ones, which is quite normal. What happens now if we take the photo not in January, but in February, March, April, May, etc.? Amazing, isn't it? It truly gives the impression that the Earth is breathing, and that this is indeed the Earth's annual breathing cycle. It's incredible, isn't it? The concept I would like to introduce now is that of engineer species. This concept comes from Clive Jones, an American ecologist who developed this idea of ecological engineering. In the first image, we see a body of water with a sort of dam. It is the construction of a beaver indeed. This is the typical example of an engineer species, that is, a species that will transform its environment to adapt it to its needs. So typically here we have a beaver dam that creates a body of water, allowing it to meet its needs, build its lodge, etc. Here we have a mangrove where the mangroves generate a completely different ecosystem that allows for the creation of a fish nursery and facilitates sedimentation, which in turn creates an ecosystem, and so on. When we look at the one from below, this time we have the Great Barrier Reef. Coral is the quintessential species that performs ecological engineering because it builds a habitat that will be used by a multitude of other organisms. Closer to home, the earthworm performs essential functions by transforming the top layer of the lithosphere. This is also very important work. And then, in the same vein, we have the now well-known examples of African savannas in particular, where nitrogen and phosphorus are extremely scarce and are found concentrated in termite mounds by the termites. And in fact, if you look at a savanna where the trees are distributed, the trees originate in termite mounds because that's where the nutrients are. So you have a sort of concentration of nutrients provided by termites for the trees. So if we go even further and take what is on the screen, these little cushions come from Australia. They are stromatolites. What does that mean? It's a strange name for bacteria that we call cyanobacteria. Cyanobacteria produce a lot of oxygen. They are algae indeed, if you will. And this oxygen, well, a long time ago, it caused quite a stir because what is called the Great Oxidation is the fact that a very, very long time ago, around 3.5 billion years ago, when cyanobacteria appeared, the cyanobacteria began, through photosynthesis, to release oxygen into the air. And then this oxygen had to reduce a whole bunch of atoms, particularly iron, and there came a moment around 2 billion years ago, let's say, when an extraordinary amount of oxygen accumulated in the atmosphere. This is what is called the Great Oxidation. This event eradicated many forms of life on the surface because oxygen is a highly potent oxidant that destroys life forms unable to resist it. These life forms plunged into the depths of the earth and are now found at significant depths. And then life as we know it today, which is aerobic life, which is life that consumes oxygen, was able to develop. You have a species whose metabolism released a waste product, in this case oxygen, an extremely violent poison for all other forms of life at the time, but which eventually, a very long time later, gave rise to all life as we see it today. In summary, regarding the main principles of the biosphere, we have seen that the diversity and interdependence of living organisms ensure the functioning of the biosphere. That matter is in constant motion within a multitude of cycles, ranging from the smallest to the largest, that some species are capable of significantly transforming their environment, and that the waste of some is the food of others, and that those which are not metabolizable accumulate and can even be toxic. So here we have, in a nutshell, a summary of the situation of our species, Homo sapiens, which has started to move matter in a multitude of cycles specific to its economy, profoundly transforming its environment, and now releasing a large amount of waste that is absolutely non-metabolizable and becoming a real pollution problem for others. So we have now reviewed the various physical and biological principles that give us a bit of an understanding of the nature of our relationship with our environment. This segment concludes, and in the next one we will look at how human activities transform the metabolism of the biosphere.